And so we invited Sybil Derrible here from the University of Illinois to share some perspectives about some of the regional and maybe even beyond that, but some challenges that are being seen by other cities that we can take into consideration as we do our future urban planning. So with that, let's welcome Sybil.
Hopefully there's a few things you're going to remember today from this presentation. Some things you're not going to like, probably some things hopefully you're going to remember. One thing you will never forget is my name, Sybil Derrible. You can Google me, there's only one in the world. The Derribles, it was a mistake in City Hall from my grandfather, so we're the only Derribles in the world. So you're not going to forget, you will never forget that. But so basically, who am I? I'm originally French. I've been here for 10 years. Really enjoying it here, but I am faculty at University of Illinois, Chicago in civil engineering. And my whole focus is on the city of the future. So how do we become more sustainable? How do we become more resilient in the future? And you'll see that one of the things that I'm doing is I'm not focusing on any one infrastructure. I look at all of them. So I was trained more in transportation, but I've moved to water, stormwater, electricity, natural gas, solid waste, more and more telecommunication, and really seeing everything together. So you'll have to be patient a little bit because I'm sure all of you know more about water than I do. But hopefully I'll still have a few insights, a few things that you might enjoy. And because I'm an engineer, I like to, and an academic, I like to talk in terms of concepts, and my concepts inevitably come either in the form of an equation or a figure. Because I'm an engineer, that's just the way it works. And this one is a figure. I'll show you the figure from a book that I read more than 10 years ago now. And it was a book that was written in 1988 called The Collapse of Complex Societies by Joseph Tainter. And he used a very normal, very well-known economics model called diminishing marginal returns, and he associated that with civilization. So let's see if, all right, perfect. So that laser pointer works. So I want to explain to you what that is. It says complexity and returns. Don't really read complexity. I just really want you to think in terms of infrastructure. And so what we're going to do here is on the x-axis, we're going to add infrastructure. And on the y-axis, we're going to look at the benefits from that infrastructure. So for example, let's say you're in Omaha or you're in Lincoln, you're the first settlers there, and you need to get your water from somewhere. Where are you going to get it from? All right, so if you're in Omaha, for example, it might be some well field, or it might be from the Missouri River, and then you'll add a lot of infrastructure right here, and you'll get tons of benefits from it, right? You're gonna go first with the lowest cost, most accessible option, the easiest, so you're gonna get tons of benefits from it. And then your city grows, and that one source is not enough anymore, so you need to build more, kind of what's happening exactly with Lincoln. And so you're going to have to add more things, and maybe you're going to have to double your system. It's inevitably going to have to become more complex, but the returns are going to have to be smaller because the best option, you already tapped it, so you're going to have to go to the second best option. And if it grows again, and then you have to, again, add way more, but the benefits, even like for every gallon of water that you're using, are getting smaller. And if you keep doing that, they get smaller and smaller and smaller. So the fact that the benefits get smaller, so those benefits, those added benefits, these are marginal returns, so the new returns that we get. And the fact that they're getting smaller and smaller means that they're diminishing, so diminishing marginal returns. And my argument is that for a lot of the infrastructure right now, we're right there, here, kind of at the end. And there's two options. Is either you change, you adapt, you evolve, you think differently, or you collapse. And that's happened both in history of mankind. With the Roman Empire is a great example of collapse. The Maya civilization is a great example of collapse. I want to come back. And here, adapt and evolved. Even the Industrial Revolution is a great example of adapt and evolve. Cities got bigger. We had access to coal. We had access to fossil fuels. And we loved it, and now we understand that it was not necessarily the best thing in the world, and maybe we have to stop using a lot of that coal and that fossil fuel. And so that industrial revolution got us to go up, and now we're here again. So it's time to think differently. One of the ways I like to talk about those marginal returns also is efficiency. Whenever we're trying to be more efficient, we're trying to do the same thing a bit better. That's okay when your system is not too big. That's okay at the very beginning. A good example that I have for you is with the road system. So at first you put a few roads, it's enough, it's good. Then you have more and more people coming in, and you start to think that, well, congestion, it's not very fluid. What do? You try to make the system more efficient. You put traffic signals. And then you have traffic signals everywhere, and it's a lot more efficient. And then you're like in LA, where you have as many roads as you can build. You have one of the best traffic signal system in the world, and you have gridlock. So what's the solution? More roads? Nah. Better traffic system? Nah. You have to change the way you think about things. It's not about being more efficient, it's about being more effective. Completely changing the way you do things, trying to be a lot more innovative. And that's where we are with a lot of infrastructure systems right now. And I'll point to one, I think, at least in water, that, let's see if you agree with me. It's one where I think the water realm is really behind other infrastructure systems. So we'll try to think about that together. What we'll try to do today is really also to think differently. There's that quote from Einstein that I love, and it's, well, so you can read it, but we can't solve problems, or we can't solve our problems with the same thinking we used when we created them. So as an engineer, I know that we've developed a lot of methods, 1960s and 70s, and a lot of them kind of drove us to the problems that we have now. So they solved the problem at the time, and they were amazing. But if we keep using the same concepts now, we're not going to solve anything because they're the one that drove us there. A good example, again, in transportation is we have traffic flow theory. It was developed starting even in the 1930s and 40s, and it was amazing, and it's great. We have all those roads now, but if you use traffic flow theory to solve your problems, it's not going to work because that's what drove us there. Another good example I have for you is, I remember Mark Zuckerberg, the CEO of Facebook, testifying in front of Congress and talking about Facebook and the problem with a lot of the algorithms, all the machine learning that feed you those advertising or those posts on Facebook, and how those really are reinforced by what you see, and so you kind of get into that mindset, into that rabbit hole. And it was saying, well, maybe what we can do is to have new machine learning to judge the current machine learning. It's like, that doesn't make sense. That those there were great at the beginning, they got you to the system that you have, but you can't solve your problem by using the same thing you used that created your problem. Right? So we'll try to think about that. And one of the things that I will argue is, well, you'll see is how do we think different? It's multi-infrastructure systems. Those infrastructure systems that we talk about, they're not independent. They're not in a silo. They all live together. And there's another quote that I love from Frank Stella. Any of you here know Frank Stella? I love to ask that question because he's an artist, and engineers usually don't like, art that much. But he's a great American artist who really started with the canvas, minimalist. And then what he did is actually he emerged from the canvas. And now if you look at his art, it's almost more like a sculpture. And he has that quote, which is for the canvas, which is the boundaries of the canvas. They have to be felt in the proper way. They're defining but not limiting. Boundaries are defining but not limiting. And I love that quote because, there it is. And I love that quote because we tend, at least in engineering, to set boundaries and to limit ourselves to those boundaries. I mean, sure, the water system is the water system. The water system is not the transport system. Sure, they're not. And as a water engineer or as someone working in water, you don't have to also become a transport expert, right? Those boundaries, they're defining, but they're not limiting. Most of the time, we limit ourselves. We don't necessarily want to learn about traffic flow theory, or we don't want to learn about power grid and the power distribution. Or, let me ask you a question. Here, how many of you at home have trash and you dispose of that trash in a dumpster every once in a while? How many of you? How many of you know where that trash goes once you put it in the dumpster? Right? A few of you, right? So do you stop your garbage truck driver and do you ask the driver, where does he go after? And when I ask my students, they don't know. It's like, I don't know, I just put it in the dumpster, and somehow when I come back, it's empty. I don't know where he goes, right? I mean, sure, there's boundaries. It's your responsibility to put it in the dumpster, but that's your boundary, right? It's defining, but it's not limiting. So let's not limit ourselves. That's the main message that I'm going to try to drive at today is just let's be a bit more curious. Again, your goal is not to tell a transportation engineer what to do or a transport policymaker what to do, but at least to be able to kind of know how those systems work. Boundaries are defining but not limiting. Boundaries are defining but not limiting. And plus, all those infrastructure systems really live in the same space. They're all interdependent. Even this morning, we're talking in the water treatment plant or the water distribution. Whenever you have a storm, somehow you test your generators to see if they work, because you don't really trust the power grid. You don't really trust the power utility to do their work, right? So we try to, again, limit ourselves, but they're all interdependent. Power, they require so much water. We didn't talk about that, but I'm sure the Missouri River somewhere is being used for cooling some kind of thermal power plant. It has to. Some of the biggest problems in Arizona right now, so Phoenix right now is actually stopped expanding. They're trying to limit how much the city grows because they don't have enough water, and they have a nuclear power plant, and they're terrified that if they don't have enough water to cool the nuclear power plant, then you have a nuclear meltdown. Right? So again, they're all interdependent, and usually we don't really invite ourselves to learn more. Even by doing education, one of my biggest problems with civil engineering right now is we always ask juniors, do you know what you want to specialize in? Do you want to go more into structural or water or transportation? And then I ask them, it's like, well, in transportation, what's the symbol for flow? It's Q. In hydrology, what's the symbol for flow? It's Q. In building science, when you look at heat transfer, what's the symbol for flow? It's Q. And by the way, they're all the same equations. Darcy's laws for flow, Fourier's laws of heat transfer, Ohm's law, they're exactly the same equation. Exactly the same equation. They're different things, but they're all laws and exactly the same. And yet we always try to silo ourselves. And that really drives me mad. So all those infrastructure systems are interdependent. And we're not going to read this, but that's where I just look at some of those interdependencies. So that's physically how interdependent they are, how the function of one defines another. But that's not it. All those infrastructure systems are also highly interrelated. So before we talked about the demand for water, here we have the demand for one day, not just for water. So the water is the one in blue. Wrong one. Blue, so that's water. So right here, that's water. We have electricity here in green. We have transport in orange, and then we have telecom right there in purple. They're all interrelated. Same thing. I talk to my transportation colleagues who tell me, well, we're trying to relieve congestion, and so we have all those policies so people can leave earlier home so that the peak is not as bad. And I say, well, that has a big impact on your electricity consumption. Do you talk to the electricity provider to see if that works for them or not, or to the water utility? So water is not as important because you have those reservoirs, or you're a bit more resilient on that end. But for power, it has a big impact, especially because power is also moving toward more decentralized, more microgrids. So it's going to have a big impact. So we just must talk to one another. And at the end of the day, infrastructure is built by people for people. Right? That's what we do. And what we want is a service. And usually as a provider, we don't really think about the end service, or we don't really think about what the people want. We think about just making sure that what we control, we give them something, and we're happy with what we're doing. But at the end, it's everything together, right? I mean, this is all interrelated, all interrelated. I have a paper that came out not too long ago where we use transportation volume, traffic volume to predict electricity consumption. And we did that with electricity because we had data, but I swear, the same result would come in with water if we had smart meter data from water, right? It's all interrelated. So trying to think more about those interrelations, and we'll talk a little bit more also about multifunctional infrastructure, soon, but not now. So here's a picture of Omaha, and so if I ask you what do you see here, I would say, a structural engineer will see the buildings, a water engineer will see the river, the stream, or maybe the slides. Maybe you'll think about some of the flows of the groundwater there. A transportation person might see, that bridge in the middle. The reality is that Omaha is all these things, right? It's everything. Again, we don't think about this. And there's solid waste there as well somewhere. It's absolutely all these things. So that meant that for me, knowing that I wanted to go that way, I had to learn a lot. And so I kept repeating this morning during the tour, I'm just someone who knows a little bit about a lot of things. But I did read a lot, so I've learned a lot about urban planning. I've learned a lot about electricity. Here's the demand curve here, the different techniques to generate power, the power grid. Here, water, I love, by the way, talking to people about the urban water cycle. Everyone knows about the water cycle, but the urban water cycle is really cool. Learned a lot about transport. So there's your fundamental flow of traffic. For those of you who did an undergraduate degree in civil engineering, here's the 4-step model. Buildings and your heat transfer, and again, that's here Fourier's laws of heat transfer, exactly the same as Darcy's law, exactly the same. Even again, some of the variables are the same symbol. Solid waste, fascinating world, solid waste. Urban metabolism is kind of the thing that puts it all together. Urban metabolism is when you look at the flow of energy, resources, water, everything within a city. And I'll talk more about some of these things. Then I'm really thinking about how do you think different, right? So we can't solve our problem by using the same thinking we used when we created them, which means that we have to sort of think differently. And that for that, I've really learned a lot about the science of cities, about network science. And I do a lot of machine learning and data science, a lot of it. And I find it fascinating. And by the way, the computer science industry, they're absolutely amazing in marketing. I mean, the first time I heard about a random forest, it's like, wow, a random forest. But it's not that hard. You can all learn what random forest algorithm does. It's really not that complicated. It's very intimidating. Let me know. I mean, I'll tell you, when you hear about support vector machine and random forest, at some point they throw the term deep learning. It's like, oh, what's deep learning? It's all accessible. You should all know kind of how it works. You can all do it, I swear. And I did it. And if I did, everyone can. So everything together, and that actually led to a book. So I'm pretty proud of that book that was published in 2019 at MIT Press. I cannot give you a copy of that book, but what I can give you if you want is a free PDF of the unformatted, unedited version of that book, if you want it. And I was saying this morning, I kind of turned that book also as a trade book. So for anyone with no equations, nothing, with 16 chapters, traveling to different cities in the world, if you want a copy of it, I can send you the PDF. As long as you don't post it online somewhere, you can have a copy of it. I'll be more than happy to share it with you. The only thing I ask is, if you find a mistake, you have to tell me. Because I don't want to cover necessarily everything, but I just don't want to be wrong. And again, I know a little bit about a lot of things, but I don't know everything. So if you read something in the water chapter, you're like, Sybil, that's ridiculous, that's stupid, that's so wrong, just email me so I change it before it gets published. All right, so that's where we are. So infrastructure design, I was even thinking about it, and the way that we design infrastructure, at least in the 20th century, is to think about, it gets so complicated that we started to create departments. So that's why now we have departments of infrastructure, department of transportation, department of water, department of housing. A lot of the times we've really pushed for higher efficiency. So we have pressure, for example, from the mayor to make sure that water quality is good. And so what we want for that is to be as efficient as possible and to control everything. We don't want to rely on other departments. Because if we rely on other departments and we can control them, then that's a hazard. So that's really what led us, all these. And same thing that really also led to those heavily centralized mega projects, go big and bold solutions, go big or go home. That's stupid. That's absolutely stupid. And I'll show you examples where going small is much better, much, much, much better. So that's kind of where we are. To a large extent, yeah, so those existing infrastructure design practices led us to over-engineered systems. One example is this one. Have you seen that before? That's in Los Angeles. Everyone knows that. Everyone who's watched Terminator 2 knows that place, right? That's where you have the scene with the motorcycle and the truck. This is ugly. This is all concrete. This is definitely over-engineered, and there's no way we do something similar today. Let's see if this works now. There's a little video, I'll press more, but there's a little video there, and someone posted it earlier this year on LinkedIn and said, oh, wow, I shot it from my hotel room. This is the city of the future. Let's see if it works. So it's a video of Dubai. Oh, there you go, it works. This is the city of the future. Oh, look at those amazing, complex expressway with all those buildings, finishing with the view of the Burj Khalifa. When I saw that, I was like, this is the city of the past. Are you kidding me? The city of the future? That's Metropolis, a movie that came out in 1927. That's what people thought the city would be like in the early 1900s. This is not the city of the future. This is the city of the past. Now we do much better than that. At least if you're in stormwater management, you're going to go for green infrastructure. You know that more green is better, right? It's better for humans. It makes us happier. It's also better for the environment. So this is the seed of the past. What I'm really hoping to do is to make sure that engineers who graduate don't see this and say, wow, cool, it's the seed of the future. Say, nah, this is bad. This is really bad. This is a traffic nightmare. There's not an inch of natural environment there. It was all men, all built by men. So, but traffic nightmare from a building energy consumption, it's probably horrible as well. So this is absolutely not the seed of the future. This is what we don't want to do. So, so please don't leave, by arguing that Dubai is a great example. It's not, and for so many ways. And again, this is exactly what we thought the city of the future would be in 1927 or even before that. Here, this is the Hyperloop by Musk. I love this example because I really like electric vehicles. I really think they're cool. There's Solar City. I really think it's cool project by him. Even Starlink is cool. This is absolutely ridiculous by adding more capacity underground, trying to make you think that you're going to zoom through a city. That's not the answer. This is totally over-engineered. This does not make sense. Absolutely does not make sense. So I love this example because Elon Musk, whether we like him or not, he's got some great ideas, but he's also got some really, really dumb ideas. I'll give you more examples again after. But the goal part of it is really to rethink infrastructure design a little bit. And again, you're going to look at me, you're going to say, well, Sybil, that's nice, but it's really not practical. Again, I know, right? But I'm thinking about the future, really trying to have a conversation, really see, the direction where we might want to go. So one of the things I was thinking about is that integration decentralization matrix, where mostly now we tend to be heavily centralized. So we like to have big water treatment plants, big power plants, big wastewater treatment plants, and we try to be separated because we don't want to depend on other departments. So that's the current paradigm. A good example for that is this. Anyone knows what that is? I'll talk more about that after, but that's the TARP system in Chicago. So in the 1960s, so Chicago, like many cities, has a combined sewer system because it was the cheaper option when it was starting to be built. And then in the 1960s or 40s, 50s, it really grew. And it got so big, and the combined sewer system was too small. And it got so big, which means that all surfaces were impermeable, right? A lot of asphalt, a lot of concrete. And so the solution that they found at the time was, all right, the surfaces are all impermeable. The water cannot go anywhere, it goes in the sewer, which means that the solution is to build much bigger tunnels underground and use those tunnels to dump wastewater whenever it rains too much. I'll show you exactly what it means after, and I'll complain about it again. But this is the TARP system. Really over-engineered, completely separated. It's all below the rivers. One of the reasons why it's below the rivers is also because the Department of Water Management owns the waterway. Maybe they could have put it below the interstate highway systems, for example, but that means they would have had to work with the Department of Transportation. Nah, we don't want to work with anyone else. We want to keep it just for ourselves. So that's the current paradigm. Now, part of it, we're trying to be a bit more decentralized, but still very much separated. And a good example for that are solar panels. So everyone can have a solar panel, very, very much distributed, right? As opposed to those massive, for example, thermal power plants like hydroelectric power plants or nuclear or coal. But still very separated but decentralized. That's one where we're going. Another one is we have a few examples of localized integration. And that's when you're still very much centralized, but at least you're starting to integrate a little bit. That example here, it's of Kuala Lumpur. And basically, Kuala Lumpur is in capital Malaysia. It's in the tropical climate. It rains a lot, so they have to deal with very intense flooding. At the same time, Kuala Lumpur has a big traffic problem. And it doesn't rain all the time, but they have a traffic problem. So what they did there is to build a tunnel, and you have traffic. And whenever it rains too much, they close it to traffic and then just flood the entire tunnel. All right? And so many cities have those tunnels, by the way, and they don't do that, right? You might have some at the bottom here, some stormwater management, but they don't. In Kuala Lumpur, they did. So, some integration, and I sort of don't like that example, but you have some integration. Another one, I'm going to show you the picture right after because I kind of want to make you think about it, is now we're going to go to India. And India has 1.5 billion people, and 1.5 billion people need to eat. So you need to provide that food somehow. So agriculture is huge in India. Now, it is also a very hot place with some water, but you have to irrigate, you have to transport a lot of that water to places just to grow all these crops. So that means that they have a lot of canals just about everywhere. But at the same time, it's really, really hot. So they had a huge problem with evaporation. What do? You have a canal that's exposed to the air. Evaporation is a huge problem. You want to maintain as much water as you can. What do? Ask an engineer of 1960s or 70s, they would tell you the problem is evaporation. You cover it. Otherwise, you put it on the ground. That's what you do. It just makes sense, right? And a 21st century engineer is going to tell you, what else can you do with it? Why don't you put solar panels on it? That's going to provide the shade, and now your temperature is going to be a lot lower, so it's not going to evaporate nearly as much. And at the same time, that cooler water under actually is better for the solar panel. So the solar panel is a lot more efficient. All right? Stupid example. It's kind of obvious when you look at it, but before you're like, well, you just cover it, you know? But when you start to think about those multiple infrastructures and how they start to integrate, and when you start to think about multifunctional infrastructure, then you see that they're a lot more, they make a lot of sense. One of the things I like to say, by the way, is that now all that infrastructure is absolutely interdependent, but it's not by design. It's just because we want it to be more efficient. One of them, by the way, now is telecom. So all infrastructure systems are absolutely vulnerable to any damages in the telecom industry. This morning we were talking about the SCADA system. You put the SCADA system because this is where you're a lot more efficient. It's great, absolutely. But now you're building also, you have a vulnerability over that telecom. Is the solution not to use telecom? Absolutely not. You want to use telecom, but do you want to use it in such a way that you make your whole system more resilient? So by having those things now it's interdependent by design, and so these interdependencies, instead of being vulnerabilities, they tend to be enabling factor because both your systems work much better, right? And again, I might have some of this wrong, but think about some of what you're doing, your institutions, think about those interdependencies, how they could be, more resilient, and think about new projects, including that new pipe that you're going to get from the Missouri River all the way to Lincoln. Is there anything else you could do with it? Right? Is there? I don't know. But is there anything else you could do with it to provide a better service for something else? And the last one is integrated decentralization, which doesn't work for everywhere, but I'm an absolute fanatic about green infrastructure. I love it. The green infrastructure is changing cities everywhere in the world. So that's an example in Copenhagen where they want to become a climate-ready city, and they turn an entire neighborhood, but that's one street here, into what's very, very traditional sort of street with here you have grass that doesn't do anything for flooding, to a climate-ready or cloud-burst street with much better stormwater management, with some green infrastructure. So that street here, it's both for traffic and for water. So you just start to think differently. And green infrastructure is a good example because you can really do it in every single street, in every single city. So not everything has to be integrated and decentralized, not absolutely everything, but you think about it. Just try to push away from the current paradigm. And I even encourage you to do that for Lincoln. Maybe there's nothing to be done, maybe not, but maybe there is. Maybe you can integrate, maybe you can try to be multifunctional. And by the way, one of my big pushes for multifunctionality is that now all of a sudden an asset is not owned by one agency, but by two, which means that you get resources and money from two agencies. So the value of the asset goes up and you have more support for it. So there we go. So now I want to focus more on water and wastewater because this is a water conference. So I was trying to think about, again, water and wastewater and what were some of the flaws, what's working well, what's not working well, and we'll start with water. The three big elements are collection, treatment, and distribution. So you know way more about me about everything, but collection, one source is surface water. So this is in Chicago. This is a crib in Chicago. It's been there for more than 100 years now. So you have those crib that's about 2 miles into the lake. And so you have an underground then tunnel that brings it to roughly here, and that's the Jardine treatment plant. And that's so because you don't want to get the water that's really near the shore. We do have combined sewer overflow as well. So you get it 2 miles into the lake, so that's surface water. Here we have groundwater, so you know that a lot. So sometimes you take the water from a well here. Sometimes I learned just that, you learned that today here in Lincoln, at least you get it sometimes just under the river, right? When you have two sources. So that's the way we do things. Here, another source now is the sea often. So desalination is becoming bigger and bigger in places that don't have much water. Israel, they have one of the largest in the world. Saudi Arabia, they're like this. This one is in Singapore, except that this is kind of a bad picture because this here is not seawater, that's fresh water. So I told that to some folks this morning. See, all that land that's here, all that land here did not exist 30 years ago. It was not there. A fifth of Singapore is reclaimed land. They just got a lot of rocks from Indonesia and they infilled the water just by Singapore. And they created that horseshoe pattern. And this all here, that is fresh water. And there's a dam that's right here. And that's the Marina Bay Sands with an amazing swimming pool here. Go to Singapore, it's an amazing place, but this is all fresh water. One of the reasons why they wanted to do that is Singapore is very small. They don't have many resources. They don't have many natural resources. They import a lot of water from Malaysia, and Malaysia likes to put pressure on them. It's like, oh, we're going to close that tap. If you're not happy, if you're not nice with us, we're going to close that tap. So they need to build those reservoirs. So that's one. There's another one on the island as well. In addition to a lot of measures that they're doing, water consumption in Singapore is one of the lowest in the world, and they're also very big on water circularity. So they treat the wastewater and then they send it to industries for industrial use, not for consumption, not clean enough, but about 25% of their water now is reused, of the wastewater is reused, and they're going to go up to 40%. So this is the sea, and they do desalinate a lot of water as well, but this is actually fresh water. So when I think about water collection, I mean, the thing is, what's the biggest problem with our water collection? I don't really know. I think we're pretty good at it because we tend to use gravity as much as possible. Even whenever we have wells, I think we're pretty good. The next step is water treatment. You also know a lot more than me. This is just a tiny little figure where we have intake, we have screens to remove the large stuff first. Depending on where you are, depending on the quality of the water, you might have coagulation, flocculation, some sedimentation, so all those flocks just settle down, so you have sort of clear water, then some filtration, and then some final disinfection, whether it's chlorine or chloramine or something else. I'm thinking about water treatment. I'm not an expert, but I really think to me, it sounds like the current process is pretty good and works pretty well. Desalination is different because it requires really a lot of electricity because you have to apply amazing pressure, 70 bar of pressure on that seawater to remove everything except for the H2O molecules. But otherwise, the current process works pretty well. It actually reminds me of, I watched a documentary on Netflix a few years ago, this one from Bill Gates. And I forget if it's the first episode or not, but they went to an entrepreneur, an engineer, to try to provide clean water to some places. Engineer was saying, well, I was thinking about what I could do, and what I can do is boil it to make it clean. And in my mind, I was thinking, yeah, but that's stupid. I mean, it's not that you don't want to boil it, but boiling it means you need tons of energy to provide that heat to boil it. There's a reason why we don't boil drinking water in water treatment plants. We try to do it in a way that's just much more, that requires a lot less energy. And in the end, what you're left with is water with all those minerals, right? So again, I think to me, and you might tell me, no, the water treatment world completely has to change. But the way I think about it is it tends to work pretty well right now. My beef is with water distribution. This is the way it works now. We have our treatment plant. We have our pipe, that distribution system in those pumps, and then they go to houses. And to me, right now, this makes no sense because we have thousands of miles of pipes that are under constant pressure, always at 50 psi, 60 psi, 70 psi, and for decades, right? It's a ticking time bomb. And then what happens? Water main break. We have to go emergency. All right, we close the valve, we change it. All right, people need their water, so we change it. And then it's constantly changing and changing, totally under pressure. That doesn't make sense. There's got to be a better way of doing it, right? This is a ticking time bomb. What's the solution? I have no idea. I don't know what the solution is. All I know is that there's got to be a better solution than having those thousands of miles of pipes in the ground that stay there for decades or sometimes even more. They're constantly under pressure, right? There's got to be a better way. One way that at some point, so this is another way of kind of showing how it works. So we take surface water, groundwater, water treatment plant, and then we have high pressure and we're sending it to a house. And so it's very, very, very vulnerable because it might break. It also requires a lot of energy. And so really that's the way we're doing it here. And then in 2019, I went to Vietnam for a sabbatical, and I learned about how everything worked there. And then they told me about their water distribution system, and I felt so dumb. I was like, this is genius. This is amazing. And so the way it works there is they had those neighborhoods in the city. They didn't have enough water distribution for everyone. So what they would do is to distribute to a neighborhood in the city and then stop in another neighborhood. But the people need water all the time. So what they did was to have basement tanks. And before, the water pressure was not high enough, so we were not at 70 psi, maybe closer to 20 psi. And then it would have the basement tanks because there's always lower elevation, so they would always get water. So then you have your basement tank there. But then you also have power outages sometimes. So they have a rooftop tank, and what they do is, at least when electricity is cheap, is they pump water to the rooftop tank. Another thing there is also it warms up a little bit, so you don't need as much energy for water heating. And then if you want to drink it, because it is drinkable after the water treatment plant, not so much when it gets to the house because you don't know if it's been contaminated, then they have point-of-use treatment. So they have some separate filtration system. And I was stunned. And I was told in India, many parts of India, they do the same thing. And I was like, well, but that's vastly superior to what we're doing. Because when I was there, one well got contaminated, so they shut down the service for a few days. People didn't care because they had their basement tank and their rooftop tank, and it worked well. And even if they have a power outage, rooftop tank, it's there on the roof, gravity, they don't care. It just sounded a lot more resilient than what we have here, and also more sustainable because you need less pressure. And so I actually wrote a paper about that, and I published it in a small perspective in a journal. And the comments that I got from the reviewers were, what about the equity problem? And I came back and I said, yes, of course, equity is a big problem because right now you're posing this, now the responsibility goes to the people, and basement tanks are expensive, rooftop tanks are expensive, absolutely. But we're talking about Vietnam. If Vietnam can do it, Vietnam is not a super rich country. If it was Singapore, I might say, well, yeah, of course, yeah, Singapore, they're small and they're a very rich country. But we're talking about Vietnam, and we're talking about India. And if they can do it here, there's got to be something that we can do here also in the US, right? I don't know whether this is a solution for the US. All I know is that the current way that we distribute water in the US doesn't make sense. And I said US, I mean most of the high-income countries in Europe, US, it really doesn't make sense and it has to change. And I really don't know where it's going, but I really think it's lagging because the transport industry is completely transforming itself right now. The power industry is completely transforming itself right now. The water industry, at least water distribution, is not. And so I'd love to get your input on that. And I was also having this discussion this morning where I do think somehow, at least for me, if you make me more responsible of my water quality, I'm probably going to be more appreciative of what you guys do. Instead of just assuming that the water has to be clean when it comes to my house, if I'm partly responsible for it, I'm partly going to be more grateful to what the Department of Water Management does in Chicago. And truth is, I'm probably going to be having fun changing stuff and filters and everything because I like to do these things. So again, I'm not saying this is the solution. I'm not saying, you're probably going to say, well, it's easy to say. It's not practical. So yeah, but think about it for the longer term, right? Because the industry will have to change. It will really have to change. And we have to think about ideas now. And I think this is one really good idea, that rooftop tank and basement tank. I like the rooftop tank as well because right now in your house, 50% of the energy that you use roughly is for space conditioning, mostly heating, but some cooling. 25% is for water heating, 25% is for the rest, computers, lights, and everything else. So 25% is for water heating. The way we do it right now is we get that really cold water around 50 degrees that's in the pipe in the street. We bring it to the water heater and we heat it up. So we have to bring it from, let's say 50 to 90. But if it's in the rooftop and it's at 70 degrees, then we'll only need to bring it from 70 to 90, for example. So, if you go, in a lot of places, you're going to see those rooftop tanks or solar water heaters. They're everywhere, just not here. So we do need to change something here. Now let's move to wastewater. In wastewater, there's two kinds: sanitary wastewater, stormwater, sewer. I learned about sanitary wastewater. I learned about sanitary wastewater. I'm not gonna talk too much about wastewater treatment. I don't know enough about it. And again, it seems to me that it's one of those things where there is innovation, it is moving in the right way, and I don't really know if it's a big problem the way we're doing things now. In terms of handling the sewer, sometimes we have a combined sewer system. That's an example of Chicago. That's your typical example of an old city where you started to consume more water for drinking and shower and cleaning and everything. You had to dispose of it because cesspools were full. Where do you put it? There were those drains already in the street for stormwater. So we just connected, and that led to combined sewers. Right now, we're not building any combined sewers. Any city that I know in the world or neighborhood outside of the old areas that are being built are all separate. But some cities still have combined, and separating those is very difficult. But that's the problem that we have right now. So you have your stormwater goes straight to the sewer, as well as all your sanitary wastewater that goes together. That's a big problem. One solution, I don't know for sure, but I'll talk more about the stormwater after. So this is your separate sewer system, which is happening in most places. Separate sewer system is much, much, much better because now your sewer pipe here, it does not overflow. So you go to the wastewater treatment plant and it gets treated and it's fine. And the stormwater here, usually it's clean enough that you don't even need to treat it. Because treating wastewater requires a tremendous amount of energy. And so if you don't have to treat it, then it's just, it's just much easier. I just want to come here. That's back to the TARP system that I talked about in Chicago before, where, so basically what they did is you had your sewer system, combined sewer system, and it would overflow to the river. And it still does now. But what they wanted to do is to build those massive underground tunnels here, massive, absolutely massive, to get some of that overflow. Then they bring all that overflow to an empty quarry outside of the city. So there's a few of them, including the McCook Reservoir that you can see if you fly to Chicago. And it stays there, and it absolutely stinks, and the residents hate it. But when it rains a lot, they don't have no choice. And then when it stops raining, they pump it to the wastewater treatment plant. And this is, for me, typically 1960s example of a solution. If I were an engineer in the 1960s, I would have probably done the same thing. But I like to bring back the problem, which is, the problem is surfaces are impermeable, water has nowhere to go, so it goes to the sewers. Is the solution to bring that to an empty quarry, or is the solution to try to make the surfaces more permeable? Right? And the real solution is to make the surfaces more permeable as much as possible. And I'll talk more about green infrastructure, but green infrastructure is not perfect, but at least, it's better than this. And by the way, I talk about this a lot in my class because these are enormous tunnels, and there's, I don't know how many miles of tunnels, but they're beautiful tunnels, absolutely gorgeous tunnels that are purely there to store poop. And it really bothers me because we have a crappy transit system in Chicago with a nice subway system, but I wish, the system could probably be doubled in size if we had built the same tunnels for people. Instead of spending those billions of dollars for people, we spend it for poop. It's not kind of true, right? Of course it's for people, but I just wish we had, just a better subway system in Chicago, because I think we'd do much better. So this is an example of green infrastructure. This is also in Chicago, where we have permeable pavers. So whenever it rains, water goes in the pavers here. We have aggregates. Chicago is clay, so it's got a hard soil. So we do have to engineer them very, very carefully because the gravel gets full with water. It overflows. If it overflows, it goes to the planters. Then you have some infiltration here. Some of that water is being used for the plants. And if it overflows, then it goes to the sewers. Maintaining those pavers is not easy. You do need to vacuum them every once in a while. They do displace. Maintaining the planters is not easy. It does require us to think differently. It does require some level of maintenance that your traditional infrastructure does not require. But we're smart people, and we learn, and we can make things better. And what I'm told is that 15 years ago, when we're talking about green infrastructure, people thought, all right, that's very nice, but I have a limited budget, and I'm just going to go with what I know. And 15 years after, it's the opposite. Now we do a lot of green infrastructure. I know in Chicago, at least, they love good infrastructure. We're still figuring out some of the designs because sometimes your retention is not great. Depends also on the freeze-thaw cycle in the winter, where we're learning. And really, I think, to me anyway, that's a much better example, because what we're doing is, instead of putting all that storm water and poop water in those huge tunnels, we just store them locally everywhere in the city. And we store them for some detail, so for some type of storm duration. And at some point they overflow and they go to the sewer. And at some point they might overflow as well, and then the city might still flood, right? It is an engineered project, but it just makes a lot of sense. And I love this, by the way, because forever, absolutely ever, humans have been just trying to get rid of stormwater as soon as possible. They have ditches. And now what we're doing is really to try to maintain those, retain those locally, and have many in the world. I see I don't have too much time, so I want to hurry up a little bit. That's the last example I want to give you, and then I'll do a few things, but I love this example. Paris. Paris is right there, and you see there's a few rivers. So the Seine River here has a few rivers to it. It's got the Marne River, the Seine River, and here there's two. In 1919, they had an enormous flood where the three rivers leading to it all had their peak, the critical duration of the peak arrived at the same time. So the entire city flooded. And they really wanted to prepare for that. So what they did was to build massive, here, absolutely massive reservoirs of water. They were not there, they built one, and here they're building the last one here. They're massive. These are your mega projects, and they're building them to be able to store as much water as possible to try to make sure that the peak doesn't arrive at the same time in Paris. But they know it's going to arrive. And there's a great documentary that I'll recommend, and I'll show you right after. But what they see in the documentary is that this is the last one that they're building because it's stupid. those mega projects are absolutely stupid. Because what you're trying to do is to have those huge reservoirs there, but they're not that big, actually, when you think about them. So instead of having those huge reservoirs there, what they're trying to do now is to locate everywhere, everywhere along the rivers what can be flooded. And they're working with farmers who have their fields, and they're locating those next to the rivers, and they're thinking about crops that they can put so that even if it completely floods, the crops are still fine. And I love the example in the documentary. So this is the documentary, by the way. So you have to write, it's in French. Literally it means when the Seine River will overflow. It is on YouTube. You can put subtitles. It is free. And for all you nerds here like me, you'll love it because you talk about everything. So I highly recommend you take a picture of this or you watch this documentary tonight. It's great. But what they're doing is, so they're thinking about, so here, right here, all those little floods, local floods here, can contain 6 times the quantity of stormwater that the 3 big mega projects can contain. 6 times. And the crops that they have, even if they're flooded, sure they can be fine. And so now they're talking with the farmer and they were trying to identify crops that could be flooded for even up to a month or 6 weeks and would be fine. And the crop they thought about, and I love it because it's such a French thing, it's mustard. So you can have mustard plants, it's flooded for 6 weeks, and then it retrieves, and then you can still use the mustard and make some nice Dijon mustard for you. So I love this example. Again, the 1960s engineer would have those mega projects, the 21st century engineers, 2020 engineers, is really trying to think of what I like, many smalls are often better than one big. Because the amount of water that can be retained, again, is 6 times what those mega projects can, right? So it's much bigger, but it's many smalls. So many smalls often are better than one big. And I know you have the Missouri River here and the Elkhorn River and the Platte River, and I'm sure sometimes it might flood, and so maybe that's something that would be good for you. So just in a few minutes now, more concept to help us think different a little bit. I'm trying to think about just really for me to get my juice going, my brain to think to be a bit more creative. One of them is, at least in the telecom industry, they focus a lot on quality of experience and not the quality of service. And I think in traditional engineering, we really think about quality of service. So we want to make sure that the water is perfect, as opposed to the experience that people have when they're home. Even this morning, they were saying at the plant, we're talking about someone who was complaining that their ice cubes were funny, just tasted funny. And then they went to the person's place, and it's because their filter in their fridge had never been cleaned. So it had nothing to do with the water. So the quality of the experience for the person was not great, even though the quality of the service was really good. My other example is with transit. So I use transit, I use the bus. And before, we used to really make sure that the buses were on time, the schedules had to be there, quality of the service. Now I have an app that tells me when my next bus comes. So if it comes in 5 minutes or 10 minutes, I don't really care. I just look at it. So the quality of the experience is much better. And for all I know, the quality of the service might have gone down, but the quality of the experience is much better. And so maybe in the water industry, we can think more about the quality of the experience. And then this is more for the telecom industry. Do you really know your download speed when you're on the internet? You don't, right? They give you a number, whether it's 50 megabytes, 100 or 1,000 or terabytes per second. Usually it's not that because it also depends on the demand. They only care about the quality of the experience, and you're probably fine. Right? So there's just ways to think differently about what we're providing. Another one is, there's a quote here that I learned. Just someone told me that this week or last week. You can't manage what you can't measure. We always say that. Well, you can't manage what you can't measure. But if you do that, then you end up managing only what you can measure. And to that point, just before the presentation before, you were saying that the solution that you found was actually one of the most expensive, but it's still the better one. I'll argue that it's probably the cheapest one. Because when you think about the social cost, when you think about the flooding, or what if there's a drought, or what if, if you add up all those costs that you didn't think about, maybe that's actually the cheapest option that you came up with, right? So you only measured a few things, but you had the logic to, we're only measuring a few things, but there's also these other things, right? So we have to be a little bit careful, because if we only measure what we can measure, then we're not managing everything. Also switching focus a little bit. I was saying that to some people this morning as well. Before, we're really thinking about how do we achieve sustainability, how do we achieve resilience. And when we think about that, usually we end up wanting to do the exact same thing, but in the ways that's more resilient or more sustainable. So we're going to do the exact same thing, but try to use less energy. What if we turn this around to have another goal? One of them is environmental justice. Now, you can't really have environmental justice if you're not sustainable, because that means that the burdens, the environmental burdens of all the polluters have to be evenly distributed. And you can't do that if they're not, if you're not sustainable, because a lot of people won't be okay with having a lot of burden on them. The planetary crisis, that's one of the, so I'm part of a United Nations environmental program team that's writing a report. It's like 200 authors writing a report for all nations in the world. And the main goal of that report is to address the planetary crisis, the 3+1 crisis, climate change, air pollution, biodiversity loss, and land degradation. And I love that because it's not just about sustainability. It's not about just stopping carbon. It's about addressing those 4 problems. And so that really gets you to think differently. Again, it's not just about lowering energy consumption. It's about biodiversity loss. What does that mean? Right? So it just helps you think differently. The other one, the last one I want to talk about is depopulation, because I have a whole project on depopulation right now. Many cities in the US are currently depopulating, really a lot. This is here currently for Nebraska. So some are increasing in population, so right here Omaha and Lincoln, but a lot of them are depopulating, and sometimes, or a lot of times, the way that we've built infrastructure isn't very, very rigid. So if a place is depopulating, that means you don't have enough resources, you don't have the same revenue to be able to maintain your infrastructure, but it's there and it has to be maintained. Those roads have to be paved. But if you don't have the money, you can't do that. Think about especially water. Think about your water system. What if it's, it goes down, and right now, again, those pipes are always under pressure, and you have someone living far away, so you can't just shut out the entire neighborhood, but you have fewer people, the bills don't pay, and you can't even maintain everything. So you have to rethink, maybe, I think what we should do is to rethink the way that we build infrastructure, and really away from that growth-based planning to a more managed planning, because many, many, many cities are depopulating in the US. So we do have a project, and we forecasted population in every single city in the US to 2100. And what we found is out of the 30,000 cities roughly in the US, about half of them are depopulating. Half. So that's a lot. That's really a lot. So we'll have to change the way that we think about things. And even Lincoln, by the way, there we go. Even Lincoln, he is increasing in population. I would invite you to think about being more modular, because right now it's increasing and it might increase for the next foreseeable future, but at some point it's probably going to shrink. And so all that asset that you're building now that's providing for people will become a liability, right? So there's just a shift. So again, that's cultural shift in the engineering community to think a little bit differently about how we do things. And that's basically what I wanted to do today. So that's all I have for you. The last one quote is from Don Norman, who wrote a book called The Design of Everyday Life. I like that quote. It's engineers and business people are trained to solve problems. That's true. I like to say engineers are problem solvers. Designers are trained to discover problems. A brilliant solution to the wrong problem can be worse than no solution at all. Solve the correct problem. And I love that because, again, at least for me as an engineer, usually we have a municipality or someone telling us what their problems are, and we're trying to find a solution. But sometimes they're probably wrong. They probably don't get it right. That's why a designer, someone's going to say, well, this is my problem. This guy's like, well, do your work. I'll watch you do your work, and I'll see whether this is really your problem or not. So try to really go to the root of the problem. That's about it. So conclusion, basically, transformation is happening. I think water is a little bit behind. Water distribution is lagging a little bit. But we're trying to move away from monofunctional mega projects toward multifunctionals, decentralized infrastructure. And then we just have to think a little bit differently. Let's try to think a little bit differently of what we do to try to address some of those problems. And that's all I have for you. Thank you very much. And I went over a little bit. I'm sorry. Well, I have a few minutes.
We do have some time for some questions.
Very good presentation. Thank you. When you were talking, a lot of what I was thinking about is as engineers, we are trained to be very risk averse, and we're trained to not risk the lives of the people we're protecting. So some of what you were talking about is there going to be a need to try to shift that, because we're trained as engineers to protect the health of people. And if we're like the decentralized systems, we're not allowed to protect the health. in the systems we're supposed to take care of. So how do you talk through those things?
100%. So absolutely, we'll have to change things. I don't think it's about being more risky, but I do think it's about being better conscious of what people actually want. As far as I know, engineers don't talk to people much. I was telling someone this morning, I love talking with high school students. They're full of energy. They're full of hope. They want to change the world. I hate talking to senior undergraduate students. They're robots. They apply equations. They don't think. And they only think technical. They don't really think about the implication of what they do to society. I was giving the example of social media. Computer scientists or software engineers build social media apps. Those apps are known to increase level of anxiety and depression. I don't think a single one of them thought about it when they were coding it, right? Because they're engineers who just solve a technical problem to be more efficient. So I think if we can become actually more people-oriented and better understand what they want and provide them the service that they want as opposed to what we think they want, or as opposed to making sure that our system works without really thinking about them, I think that would be much better. Because sometimes maybe the decentralized solution makes no sense, absolutely. And sometimes maybe it does. And right now we're just so focused on the technical aspect. The other example I was talking about was there's a podcast called Revisionist History with Malcolm Gladwell. And he has an episode a few years ago on the 9/11 memorial. And he was talking about the memorial and how it's so complicated. And below the memorial, you have the entire transport hub that even they have a lot of trees, 300 trees. They had to engineer the soil of the trees to be ultralight, not to put too much burden. And that was $40 million just for the soil of the trees. And engineers were probably like, cool, let's work on that soil to make it super light. But if you're more of a moral philosophy person, you're like, $40 million, is it really worth it? Should I go and talk with the architect? Should I maybe just rethink whether I should do it or not? So I think shifting priorities, not to be more risky, but to make sure that we provide what people want as opposed to what we do now. I think that's where we're going. Because we don't want to hurt people, of course, right? But I mean, we've done a lot of good things, but people are still hurt, and we're really good, right? We're amazing engineers. We're talking this morning, we can build whatever we want right now. There's almost nothing we cannot build. And yet, people are still, a lot of them are still miserable. So we have to think differently.
Another question.
I'll tell you one thing. Again, email me as much as you want. If you want a copy of that book, let me know. Sometimes I don't get questions because people are like, yeah, all right. You keep thinking, but a question might come after. You might be interested to something after. So make sure to email me. I respond to emails, I promise. And again, Derrible. How can you forget that? Derrible.
One last chance. Very good. Well, we're going into a break. So if you think of it over break, definitely take the time to continue the conversation. With that, let's thank Sybil again.